graphs of y equal r sine omega t plus and minus alpha. Now, we want to find out what this graph is about, or the function is about, and what are r, omega, t, and alpha. You probably have seen this function in your trigonometry course. All right, so let's see something here. I have the graph plotter, GeoGebra here. I want to look at the graph of, first of all, let me extend the diagram so we can see all of GeoGebra here. All right, first of all, let's say we have this graph. Let me do a little thing here, set up my hardware. All right, we have y. No, we have to put y. We have sine, open bracket, x, close bracket. That's the graph of y equals sine x. We want to make a few changes to this, so let's make the original color a green color, the graph of this, and let's make it thicker. And we want to see which graph this is. Alright, so this is f of x is equal to sine x. Let's put in another graph now. Let's say we have 2 sine open bracket x. Oh, let's put the sine closer. All right, good. Now, this other graph, let's keep it the color black. I want to make it thick. I want to see which graph it is. Nice. So here, we can see the original graph, the green graph, is y equals sine x. But the original graph, the second graph, is y equals 2 sine x. What do you notice? You notice that, well, first of all, remember, from 0 up to the top is a positive amplitude from 0 to maximum value. From 0 to negative maximum is a negative amplitude. But the amplitude has doubled. Sine x is the green graph. This is the height. But the height, the amplitude of 2 sine x is twice it. Interesting. Let's zoom in a bit and do a little thing here. Suppose instead of having 2 sine x, I make an adjustment to it and have 0.5 sine x. What to that? Okay. You see what happens here though? The modified graph, the black graph, is now half the amplitude of the original green graph. So this is 0.5 because of that. Suppose we use 3 sine x, what would happen? So the original graph, y equals sine x, which would be like y equals 1 sine x. You have it at 1, it goes to a maximum of 1. But the modified graph, the black one, y equals 3 sine x, it goes to a maximum of 3. So r here represents the amplitude. So let's make a note of that. R equals amplitude of the graph. Alright? And just as a quick reminder, if you have the graph, remember, going up here from 0 is the amplitude, or down. Remember, going from positive maximum to negative maximum is the peak to peak amplitude. Alright? Remember that. Also remember, if you have the graph like this, let's say you run the graph and say this is what I call sine x. Wherever you start, and it goes through all of these processes, it goes up from maximum, reach maximum, goes down, back to 0, down to minimum, and so on. And that goes through a cycle, and it keeps repeating itself. The cycle goes from 0 to maximum, maximum back to 0, 0 to minimum, minimum back to 0. Then it goes from 0 to maximum again. What happened here is repeating and starts happening again right here. This is one cycle. And remember that the number of cycles that happen in 1 second is called the frequency. Alright? How frequent it happens. And it's measured in, you remember, hertz. I think the full name of a gentleman was Lorenzo Hertz or something like that. Usually written HZ. Yeah, this is Z. Sometimes I put a little cross on my Z so that it doesn't look like 2. Alright. And how long it takes for one cycle to be completed is called a period. And it's measured, of course, it's time, so it is in seconds. Sometimes they use uppercase T to represent the period of the graph. Alright? So just a quick reminder of these things. Now, let us let's see now. Let's keep R at 1 now. We're going to go back to the original graph. And then we're going to change omega and see what it is. So let's go back to this. If we say this is sine x, okay, we see we have it lying down on the original graph. It's the same graph. Well, let's make a little adjustment here. Let's say we have 2x. What would happen if we have sine, open bracket, 2x, close bracket? Okay, you see that? Let's look at what happens here. The original graph, it starts from here, goes the green graph, that is, it goes from 0 to maximum, maximum back to 0 here, to minimum, go back to 0, right here. So between this point and this point, you have one cycle. But the modified graph goes from 0 to maximum, back to 0, down to minimum, back to 0. It happens. And then it does the same thing again. Goes from 0 to maximum, maximum to 0, 0 to the minimum, minimum back to 0. It happens 2 times. So, whatever happened with the original green graph between this point and this point, the modified graph, sine of 2x, it doubles. It happens 2 times. So, what you have done, therefore, is double the frequency. Alright? it goes through 2 cycles when the original graph went through 1 cycle. So you double the frequency. Suppose we say 0.5. We have the frequency. We're considering a cycle as going from 0 to maximum, back to 0, then to minimum, back to 0. And then it repeats 0 to maximum, back maximum to 0, 0 to minimum, and then to 0. Right? Even though going from maximum down to 0, then minimum, then back to 0, then maximum, from here to here, it completes 1 cycle. This thing, this cycle of activities, it would repeat itself. Right? From here to here is a cycle. Whatever pattern it goes through, once it ends and starts repeating itself, it goes through a cycle, right? Remember that. But guess what now? We halve the frequency of the original graph, the original green graph, and this is what happened with the modified black graph. When the green graph went through 1 complete cycle between here and here, the modified graph goes through only half of that cycle. Right? Now, let us say we have 3x. You see, when the green graph goes through 1 cycle, the modified graph goes through 1, 2, 3 cycles. See that? 4x. The original green graph goes through, it goes up, down, back to 0, and then start again. 1 cycle. Let's see how many cycles the modified graph, what I call 4, it goes through. Goes through up, down, 1, 2, goes up and down, 3, goes up and down, 4. So we can be confident that omega is the frequency. Alright? So let's see what happens here. Let's make a note of that. Omega, Greek letter omega, is equal to frequency. Alright. Now, T, the time. You can't control time. It's like the angle. So we leave that alone. But what we can change is the alpha. What does alpha mean? Alright, let's go back to the graph. Let's put it back like the original graph. Y equals sine x. We have the black graph laying down on top of the green graph because they are the same graph. It was not modified, but let's do a little modification. Sine x. In the bracket we have plus 1. What would happen? Guess what? You see, the original graph, it cuts at the origin, but the modified graph goes to the left 1 place and cuts here. Right? Let's do a little thing and say we want plus 0.5 instead of 1. What would happen? You see that? Right? The original green graph cuts the origin at 0, but the modified graph, when you say plus 0.5, it cuts at negative 0.5. So it's like the graph moves to the left. Now, when you say plus 0.5, it moves to the left. Suppose we said minus 0.5. What would happen? minus 0.5. It moves to the right. Alright? It moves to the right. Now, when you shift the graph to the left and right, that is known as a phase shift. Alright? Let's see something here. Let us move the modified graph and watch the equation for it. Shifting to the left. Oh, I'm moving up a bit. That's why you see the minus 0.2 up and down a bit. I'm not able to move it that straight. Let us try and get it back to what it was originally. Alright, so let me see if instead of using the mouse, I can use the keyboard and see what would happen. Right, okay. Oh, it shifts. Alright, so notice as I press and the black graph move, watch the black equation. Points negative 0.7, negative 0.8, negative 0.9, negative 1. Let's move to the left and see. I'm moving to the left. It's plus. Once it passes the zero line, let me kind of shift this graph out of the way so you can see it clearly. Once it passes the zero line, right, it says plus. Now you may be saying that, how is it that when it goes to the right it's minus and when it goes to the left it's plus? You can consider, for example, you're standing on the original, or you're sitting on the original green graph. I don't want it to move and you drop off. Let's say it is a green graph moving and it moves to the right. And you look sideways, it look like the modified graph is moving back. It's like when you're in a motor vehicle and the motor vehicle is driving to the west. Or when you look back, the trees and buildings seem to be going to the east. Something like that, alright? So, what you see is when it says sine open bracket x plus or minus alpha, then alpha is the phase shift, where if you move it to the right, a minus alpha would move it to the right, and a plus alpha move the graph to the left. Alright, so that's what we have. Now, let's look at a few graphs which I have saved. Let me copy this and paste it here. When you look at this graph, for example, this is showing 0.5 x. The modified graph only goes up halfway. The original graph is saying y f of x equals sine x. The half x brings it down to half. You see that? In fact, we can take a look at all of these graphs here. Let me increase the zoom. Alright, so what you have, the green graph is sine x, the modified graph is half sine x, the black graph modified half sine x. Now, if we go to the next graph, the original graph is sine x, but the modified graph is 2 sine x. Alright? I'm not able to see the thing there. Okay, good. We're now able to see the function. Actually, 2 sine x. Alright? Because you can see this goes up to 1, the modified graph goes up to 2. here, we have doubled the amplitude from 1 up to 2, so it's twice as high. We had also doubled the frequency, 2x. So you notice the black graph goes through, oh no, let's go back to here, yes. Let's do that again. All right, the black graph, it's the original graph, right, was 1 high. The modified graph was 2 high because of this, the amplitude. This now, the original graph, it goes through one set of changes between 0 and, this would be 2 pi, 6 point something. It's in radians, right? But when you say 2x, what happens with the original, the modified graph? It went through one set of swing changes here, and then it does it again here. 2 set of changes. And when you say plus 1, you notice when the original graph cut at 0, right, you shift the modified graph. It doesn't cut at exactly 1 because of the doubling of a frequency, right? Now 4 times you see more frequency here. You're looking at sine x versus 2 sine x. Double the amplitude. In other words, you double the height or the depth. So that's what you have there. We have 0.5, sine of 0.5x. You have the original green graph, goes through 1 cycle here. The original modified graph goes through only half a cycle, right? So when the green graph goes through 2 cycles, the modified graph goes through only 1 cycle. When the original graph goes through 1 cycle, the modified graph goes through only half cycle, 0.5x. 2x here, sine 2x means you double the frequency, right? 3x, you triple the frequency. The set of changes for the original graph, notice, for example, this goes from 0 down to minimum, then back to 0, then up to maximum, then back to 0. And then it's ready to do it again, to go down from 0 to minimum and so on. The modified graph, it went down from 0 to minimum, back to 0, up to maximum, then back to 0. That's once. Down from 0 to minimum, back up to 0 to maximum, then back down to 0. That's twice. Down from 0 to minimum, back up to 0, then up from 0 to maximum, then back down to 0. That's 3 times. So it does it 3 times, 3x. Right? You triple the frequency 4 times here. Right? Alright, so here you get the idea. So therefore, what you have here is a case where whenever you have y equal r sine omega t plus or minus alpha, r represents the amplitude, omega is the frequency, and alpha is the phase shift, where if you say plus alpha, the graph will shift to the left. If you say minus alpha, it will shift to the right.